Now, you'll not be surprised to learn that there are ways of generalizing what we've just talked about for functors. And one way of doing it is to build what's called the applicative type class. Now, applicative takes the idea of the way we moved from map to zip with. If you remember, with zip with, we had two lists and a two argument function, and we applied that function to corresponding elements of the list. So we took corresponding elements, applied those functions to those pairs, and built a list of the answers that we found. So we traverse the data structure simultaneously and apply f to anything of type A and B we can find. And that, you can see, is generalized to this lift A2 function that you see here. We have a function from A to B to C, and it takes a g of A and a g of B and gives us a g of C, just as zip with took a list of A and list of B and gave us back a list of C. So we're concentrating on this function. We'll talk about one of the other functions in a few slides' time. Okay, so obviously, because I've talked about this generalizing zip with, we can think of writing an instance of applicative for lists. But what else can we do? Oh, and by the way, applicative builds on functor. So we only look at applicative type functions G, which are already functors. Well, the maybe type again comes in. Suppose that we have, we're lifting a function f, and we take two arguments of type maybe A. Well, if we have a just x and a just y, we can apply f to the x and y and return a just fxy. Now, in every other case, we don't have something of both types A and B, so we just return nothing. So if both the values are defined, both the values are not nothing, we can produce a result. Otherwise, we just produce nothing. We can also do this for trees. So here we have the case, I've put the leaf cases first. If you've got a leaf on the left, there are no values on the left-hand side. If you've got a leaf on the right, there are no values on the right-hand side. So in both those cases, we return a leaf. And in the node case, we have two nodes. We have a value x of type A and a value y of type B. So we can apply f to those, giving us fxy of type C. And then we recursively, on the left, we recursively apply lift A2 to lift A2 of f to T1 and S1, the left subtrees, and on the right we apply it to T2 and S2, the right subtrees. So only in a case when there are corresponding values of type A and B are we able to apply f, otherwise we simply return a leaf. Now, we can think of it, we can define it in another way, and this is the angle bracket star angle bracket, that says actually we can think of applying a structure of functions to a structure of arguments. So we traverse the function data structure and the argument data structure, and we apply a function that we find to an element of type A that we find. And let's see how those definitions work out. Well, in the case of maybe, if we have just of f and just of x, we can return just fx, and otherwise we return nothing. And in the case of a tree, if we are in the case where we have a node on both sides, so there'll be a function on the left-hand side and a value on the right-hand side, we can apply the function to the value, make that the value at the new node, and recursively build that function, apply that function to the left subtrees T1 and S1 and the right subtrees T2 and S2. So that's the way that this other applicative operation works. It's a sort of applicative application, if you like. It's applying a structure of functions to a structure of arguments, of values. Now, for lists, we'll see that there are two ways we can define lists as an instance of applicative. We can traverse the data structures simultaneously, applying functions to arguments, or we can just traverse the data structures not simultaneously, just pulling arguments and functions out willy-nilly and then returning the result. So in the first case, the one that's presented first, we run along the lists in lockstep. We take the first element, which is a function, the first element, which is an argument, apply the function to the argument, and then recurse. But in the other instance of applicative, we take every possible function from the list and every possible argument from the list of arguments, and we apply the function to the argument. So that takes all possible combinations of values from the first and the second. So which is the correct one? Well, the answer is that the one that fits more with what we want to say later is the second one, and it is the basis for on which we build our explanation of, or an explanation of, how lists are a monad. And that's what we're going to talk about in the next segment. What are monads and how are they defined in Haskell?